All right, so now I'm gonna do some stuff. So I think I'm gonna show. Let me just say something really quick about the the algebraic integers. Okay, so or not the algebraic integers, the algebraic numbers over Q. So there's a special field. So this is about the field Q bar. Okay, so Q bar. So there's many notations for this field, and everyone likes to have a big flame war over it. So there's Q bar, there's Q alg, and there's QA. And if you're like really crazy, you might want to do like Q tilde or something. Okay, so these are all the same thing. So all of these are the same thing. All the same. And they're the algebraic closure, right? So let me give the definition. So definition. So okay, and I'm going to give one definition. So Q bar. So this is defined to be the set of alphas in C. So that alpha is algebraic over Q. Okay, so this is what's called. So the algebraic closure of Q. Okay, so this is the algebraic closure of Q. Okay, so this contains all the algebraic numbers, field containing all the algebraic numbers. Right, so in particular, we have that some alpha is in Q bar if and only if there exists some f of x, a polynomial with q coefficients, such that so this is some polynomial. So in such that f of alpha is equal to 0. Okay, so that's what the definition is. And so what's in here? Square root of 2, square root of 3, square root of 2 plus the square root of 3. Okay, we'll get to that in a second, why that's still algebraic. I don't know, the fifth root, the third root of 5 times I, any of the roots of unity, so what's not in here, so these are all elements of Q bar. Things that are not elements, so minus square root of 2 plus 1, okay. So these are elements of Q bar. So numbers like pi, these are big theorems though. Pi, E, this is not an element of Q bar. I think it's conjectured, or I don't know what the status of this is. I think so. There's this Euler gamma, right? That's not in there. So I think this is not in here as well. So these are hard theorems. So these are hard theorems. So proving something is not algebraic is a bit of a mess. Okay, so so these are the set of algebraic numbers. Okay, so now I'll go to in a little bit later to say why these are a field, but I just wanted to kind of give you a proof of something. So let me make a theorem. So you would think that like there's lots of them, right? So that there's lots and lots of different algebraic numbers, and that maybe they're like dense, right? I mean, they are dense, but they're countable. Let's do it like this. Q bar is countable. Okay, so let's do the proof of this. So the proof is a Cantor argument, right? So the idea is that Q adjoin X is countable. Okay, and every element in there is a root of one of these things. So Q adjoin X is countable. Okay, so how do we do this? So we use that. Q is countable, right? So this is by Cantor's theorem. So this is this diagonalization argument, and then we'll just diagonalize again, right? So we say, so that we have a bunch of rational numbers, R1, R2, R3, R4, right? And so this is equal to the set of Q, right? Then so then we write down all the polynomials like as follows. So we do, so now I just need to write. Okay, so now let's write them down. So one. Okay, so now we're going to do another diagonalization argument, right? So there's countably many. Okay, so there's countably many countable collections. So there's countably many of degree 1. So let's do this. So for degree 1, there's countably many. So that looks like, R plus SX, right? Let's do this, S0 plus S1X. So you just need to show that, so Q cross Q is countable. So this is countable. Right, so degree 2. Right, so this is S0 plus S1X plus S2X squared. So we're just using that Q cross Q is countable. Right, and then we just keep going like this. Okay, and then the strategy is as follows. So we and I'll just kind of just do it really roughly, is that we're going to count like this. So we count 1 here, then we move down. Then we count 1 here, then we move back up. Then we count 1 here, 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 and then we go back, and then eventually, right, we're going to keep winding back and forth, and then we'll hit every single one, right? So winding back and forth. Like this allows us to count all of them. Okay, and then at each stage, so what we'll do is we count. Okay, so now how do I write down the roots? So I've written down a way to enumerate all the polynomials. So this gives us a procedure. Okay. So what does this do? So this gives us a procedure, a way to count Q adjoin X. Okay, so that's saying that Q adjoin X is F1 of X, F2 of X, F3 of X, and so on. All right, so then the next phase is that what we do is we just adjoin. So to count QBar, so okay, so let me just write this down. So this gives us a way. I'm recording. Yeah. Okay, so this gives us a way to count Q bar. So what we do is we go to F1. So we take all the roots. So we'll do all the roots of f1. Then we do all the roots of f2, so on. And then this is a countable procedure, right? So we just do that. It doesn't matter what order we take them in, but that'll give all the roots. All right, that's all I wanted to say. Just wanted to say that QBar is countable, and that's pretty, and it's just a diagonalization argument.